like, share, subscribe.
Hey y'all, so today we're going to be reviewing our unit on exponential functions where we talk about all the different properties that exponents have, how to simplify expressions with exponents, but also how to graph exponential functions, how to tell the difference between exponential growth and exponential decay, and also look at a few applications of exponential functions. So let's get started here. This first section is all about simplifying expressions that have variables with different exponents. Number one, we have 2 to the negative third power times x to the 0th power times y to the negative 4th power. So the first thing I notice is that we've got something that is to the 0th power, and anything, well, just about anything, other than 0, I suppose, but everything is going to be, anything raised to the 0 power is equal to 1. So I'm just going to kind of cancel that out with itself, just write a 1 over it and just kind of put it out of my mind, because anything times 1 is just itself. Then I notice that I've got these two powers here that have negative exponents. So anytime that you've got an expression with negative exponents, you want to try to rewrite those with positive exponents. And you can do that by moving the term over to the other side of the fraction. So for instance, this 2 to the negative third, I can rewrite as 2 cubed as long as I put it in the denominator. Similarly, the y to the negative fourth, I can put it up in the numerator and change that exponent to be positive. The only thing really left to do at this point is going to be to simplify the 2 cubed, and 2 cubed is 8. So we should get y to the fourth over 8, and that's about as simplified as we can get for number 1. For number 2, we've got 12 times c to the negative 7th power times d to the 6th power. Not really much to do here, except we do have that negative power, or the negative exponent on c to the negative 7. And so we want to rewrite that. Now we don't see a fraction here, so when I say move it to the other side of the fraction, you might be wondering like, okay, well, where is it supposed to go? But really, anything that doesn't have a fraction up front can be written as itself over 1. And so we're just going to put the c to the 7th in the denominator. We're going to essentially just make ourselves a fraction here. And so this should be 12d to the 6th over c to the 7th power. Number 3, we've got negative 4x cubed, and all of that is being, negative 4x squared, and all of that is being cubed. So whenever something's being cubed, that means that you're multiplying that, whatever's inside the parentheses there, by itself 3 times. So I'm just going to go ahead and write it like that, where we have negative 4x cubed, and I'm going to write it a total of 3 times. Make sure that fits on there. Okay, good. So now we can go ahead and multiply all the coefficients. Okay, so we've got negative 4 times negative 4 times negative 4. That's going to be negative 64. Feel free to check that in the calculator. And then we've got x squared times x squared times x squared. And so when we're multiplying powers that have the same base, like this one just has x squared times x squared times x squared, anytime you're multiplying these powers that have the same base, you can combine them by adding the exponents. So 2 plus 2 plus 2 would be 6. And so we would get, as our final answer here, negative 64 times x to the 6th. And that's it for number 3. Let me scroll down here. I think my head's covering up the next one, number 4. So here, there really is nothing to do. We don't have any exponents that are negative. We don't have a coefficient on the numerator that's not 1, so we can't reduce the coefficients at all. And there's no like variables, so there's nothing to combine. So really, like, this is our answer. It's already simplified. So yeah, nothing for really for me to explain there. Let's just go on to number 5 here. So number 5, there is some stuff we can do to simplify this. The first thing that we can do is multiply the coefficients of these two terms. So we can multiply 5 times 3. That's going to give me 15. And then I'm going to look at my like variables here. So I've got two different powers of a. I've got a to the 6th times a squared. And anytime you're multiplying powers with the same base, you're going to add the exponents. So 6 plus 2 would be 8. So this would be 15 a to the 8th. And then for the b's, we've got b times b squared. Now, anytime you see a variable that does not have an exponent on it, the exponent is assumed to be 1. So 1 plus 2 would be 3. And so we'd have 15 times a to the 8th times b cubed. For number 6, what do we have here? I notice, okay, so this one is going to have some things that we can simplify. So first things first, I notice that we've got this 5 over 10, and we can reduce this by dividing both of those numbers by 5, and that will give me 1/2. So this is going to be, I'm just going to write the 1 for now, even though I'll probably end up erasing that later on. But I'm going to rewrite that 5 over 10 as 1/2. Then I notice I've got this, this x cubed here, not x cubed, but x to the negative 3rd power. And I want to rewrite that with a positive power, so I'm going to move that up to the numerator. So in the numerator now I've got x cubed y squared, and then in the denominator I've got y to the 6th. So I can reduce these y's because I've got 2 y's being multiplied in the numerator and 6 y's being multiplied in the denominator. So just to really showcase like what's happening here, I'm going to not write that 1 anymore. But what I'm going to do is I'm going to expand out the y's. I'm not going to do that with the x's because I don't have anything to cancel out anyway. I only have x's in the numerator. But for the y's, I've got 2 y's up top and 6 y's in the bottom. And so you can see that 2 of these y's, or we'll have 2 pairs of y's that we can reduce to 1. So like y over y is 1, y over y is 1. So we get 2 of those y's to cancel out, which is going to leave us with 4 y's in the denominator. So our final answer here should be x cubed over y to the 4th. So yeah, there's number 6. Now that's the end of that section. So you can expect on the test there'll probably be a couple questions that you have to simplify these expressions. So let's go on to the next section here. It says for each of the following, classify them as either being linear, quadratic, or exponential. So I'm just going to run through these and kind of explain how I know what it is. So for the equations, if you have something that's x squared, and if 2 is the largest degree that you have, then that's going to be a quadratic. That is not going to be exponential. In order to be exponential, you need the x or whatever variable you have to be in the exponent. So b is y equals 3x. Now the degree on the x is 1 here. This is kind of like a y equals mx plus b equation. This is going to be a linear equation. It'll have a constant rate of change. Number 3, we notice that we've got an x in the exponent. That's how we know that this is going to be an exponential equation. Now for the tables, we got to do a little bit more digging. Like with the equations, you can kind of just look at the equation, and if you know what to look for, there's not really any arithmetic or anything like that to do to figure out the answers. But with the tables, we do have to look a little closer at what the pattern is. So like with D, I'm noticing my y values, like going from one y value to the next. When my x increases by 1, the pattern here is that I'm multiplying each y value by 5 to get the next one. So whenever you have a pattern in your table where for each increment of 1x, you're multiplying by some constant amount, in other words, like you have a constant multiplier, that is telling you that you're going to have an exponential function. This is different than like a linear function where instead of multiplying by the same number every time, you're adding the same number every time. And we see that pattern happening here in letter 7e, where to get from 12 to 14, I have to add 2. From 14 to 16 I have to add 2, and so forth. So if you're adding the same amount every time, it's going to be linear. If you're multiplying the same amount every time, it'll be exponential. And it's been a little while since we talked about quadratics, but since that's the only other option here, if it's not one of those two patterns, it has to be quadratic. And we see on F, we're either like adding 3 and then adding 1, so I don't have that linear pattern. If I think about like multiplication, I'm multiplying by 1/4, but then I'm multiplying by 0, right? So I'm not adding or multiplying the same number every time. So just using process of elimination, this is going to have to be quadratic. But just to briefly show you like how to know, like let's say I didn't just give you these 3 options and I wanted you to classify this anyway. To know it's quadratic, we can notice that, hey, yeah, I am adding 3 here. I am adding 1. And then, what am I doing here? I'm adding 1 again. And then, oh, no, I'm subtracting 1, sorry. And then from here, I'm subtracting 3. So you might not like see the pattern right away, but to know that it's quadratic, here we go. Here's what you do is you look at something called the second difference, and then you try to find basically the pattern of the pattern. So to get from 3 to 1, I'm going to subtract 2. To get from 1 to -1, I subtract 2. And to get from -1 to -3, I subtract 2. So if the first difference is constant, it's going to be linear. But if the second difference is constant, it'll be quadratic. And you can actually generalize that further. If the third difference is constant, it'll be cubic. Or if the fourth difference is if the fourth difference is constant, then it's quartic and so forth. Wow, that was a kind of a mouthful there. But anyway, so yeah, F is going to be quadratic. When you're looking at the graphs, a linear function is going to be one that has a straight line, so we can see that G is definitely going to be linear. Anytime you've got a parabola, that is going to indicate we've got a quadratic function. And then this function, this graph we see over here in I, this is an exponential decay function. So just generally, we're going to call it an exponential function. So there you go. That is going to be how you classify these equations, tables, and graphs as either being linear, quadratic, or exponential. So that wraps up the first page. Let's look at the next page. Here we're given a function rule and are asked to create a table for this function, graph it, and analyze it. So these exponential functions are going to be written in the form a times b to the x, where a is your y-intercept, so I can see that my y-intercept is going to be at 8. I can fill that out in the analysis column, but I can also fill that out in the table column. The way it's represented graphically is that we're going to plot that y-intercept of 8, but I'm going to hold off on actually doing the plot until I have all of the table filled out, because I might need to rescale this. These exponential functions, they grow really rapidly, and so I just want to make sure I can plot as much as I can on here. So I'm just going to pump the brakes on the graph here. So yeah, my initial value here is going to be 8. The constant multiplier, that's going to be the number that you're multiplying over and over again. That's going to be your b. So the y-intercept, my initial value, these are referring to the a value, and then the constant multiplier is going to be the b value. And so here the constant multiplier is going to be 0.25. Now, since this b value is smaller than 1, we know it's decay. Okay, so if the multiplier is bigger than 1, it's growth, but if it's smaller than 1, it's decay. So since this is smaller than 1, we can say this is going to be decay. Now let's go ahead and fill out the table so that we can actually plot the graph. So since our multiplier is 0.25 or 1/4, we can multiply 8 by that, and 8 times 1/4 is going to be 2, and 2 times 1/4 would be like 2 divided by 4 is going to be 1/2. And you can follow that pattern backwards to come up with the y values for each of the negative x entries. So instead of dividing by 4 to move forward, we can multiply by 4. And so we get 32, oh, not 34, let's erase that, 32. And then 32 times 4 would be 128. And so now when you're doing the graph, you do want to rescale it if you need to, but you don't necessarily need to plot every single entry in the table. So like we don't need to necessarily go up to 128, but I do want to at least try to fit 32 on there. So I think what I'm going to do here as far as scaling is scale my y-axis so that I go by 4s instead of just by 1s. So I'm just going to label these 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. Again, I'm not going to be able to fit every single point on there, but this will at least give me the majority of the points. Now, if you don't label one of these axes, I'm just going to assume that you're going by 1. But just to be clear here, I am going to go by 1s on my x-axis. Okay, so now that I've got all that labeled, I'm going to go ahead and start plotting points. So I've got negative 2 comma 128, it's not going to fit on there, but negative 1 comma 32 is. So I'm going to plot that point. Let's actually use a different color here so it can stand out a little bit more. And then 0 comma 8 is going to be way down here. 1 comma 2. And then 2 comma 1/2. Now we get to play connect the dots here. And make sure you don't cross over that x-axis. I kind of just did, just because I messed up there. You really do not want to cross that x-axis. You want your curve to just sort of ride the x-axis. Really what's happening is the function is approaching the x-axis and always getting closer and closer to it, but it never actually gets there. This isn't exactly the greatest sketch because it kind of looks like it's bouncing off. Let me try to see if I'll give it one more shot. But basically I'm going to try to make it so it looks like we are always getting closer to that x-axis rather than curving away from it. And that's probably as good as I'm going to get trying to graph this by hand. Okay, so that's that one, totally done. Let's look at the next one. Now in this next one, we're not given the equation. Instead, we are given the tables. Let me scroll down here so you can see it. So we've got to figure out the equation, but I want to do a little bit of the analysis up front. So notice how the first thing I see is that my y-intercept here is going to be 3. So I'm going to write that over here, 0 comma 3. Again, I'm going to hold off on the graph. Actually, I don't need to hold off on the graph because I already have all the tables. So I'm looking at these numbers, and I got to go all the way up to 12. I'm comfortable leaving one of these points off, I think. So I think I'm just going to scale by 1. So I'm not even, I'm going to write it on here just so that I'm being clear. But really, if you're going by 1s, you really don't need to write the scale on there. I'm just kind of doing it, I don't know, for fun, I guess. It's going to be assumed that you're going by 1s unless you specify otherwise. But I'm going to go ahead and plot these points on here. So I've got 0 comma 3, 1 comma 6, 2 comma 12, so it's going to be a little off the graph here. I might just throw in a point here just to kind of show that it's going to be up there. And then let's go to the negatives here. So negative 1 comma 1.5, and then negative 2.75. So yeah, we get this exponential growth equation going on here. But let's fill out the rest of the analysis and come up with the equation. So the initial value here is going to be 3. And the constant multiplier here, well, now that we got to figure out what that is. So like we have to think about what do we need to multiply any of these y values by to get the next one. Now, if you're ever not really sure what it is, like this one's pretty obvious. 3 times 2 is 6, times 2 is 12, etc. But if you're not sure how to find that constant multiplier, one thing you can do is just pick any of the entries and then just divide the y value by the previous entry. So like if I can't figure out just quickly that, hey, this is times 2, I could just pick any of the entries, like 6 divided by 3, and 6 divided by 3 is going to be 2. That's going to be our constant multiplier here. Since that number is bigger than 1, we're going to go ahead and say that this is growth. And we can write our equation. Y equals the y-intercept, which is 3, times the multiplier here, which is 2. So it should be 3 times 2 to the x. And that's how you're going to write an equation and graph an exponential function given a table. All right, let's look at number 9. We've got a multiple choice item here. It says a student used f of x equals 5 times 1.012 to the power of x to show the balance in a savings account, to show how the balance in a savings account will increase over time. What does the 5 represent? So that's our initial amount. That's our y-intercept. So that's going to be our a value, the initial value. So just looking at these answer choices, let's see what's going on here. The interest, the savings account earned, no, that's not going to be right. The annual interest rate for the savings account, nope, it's not that one either. The number of years it has earned interest, not that one either. The starting balance of the savings account, that's really the only one that's even close to making sense. So yeah, our answer here is going to be D. Number 10, we've got a population of squirrels that is increasing by a rate of 7% each year. So first, let's write an equation. So let's go back to the problem and kind of identify what is going to be the A and what's going to be the B. So our A value is going to be 550. That's our initial amount. Now, as far as the B value is concerned, we have to be a little bit more careful. It's not going to give it to us explicitly, but what it does give us is the rate increase. So it's increasing, it's going to be a growth equation at a rate of 7% per year. So 7% as a decimal would be like 0.07. So when you have a growth equation, the way to calculate the B value is going to be 1 plus the rate, written as a decimal. If you have a decay equation, this would be 1 minus the rate, and I'm sure we'll come up to a problem where we have to use that as well. So for growth, it's 1 plus the rate, and in this scenario, it's 1 plus 0.07. So the B value is going to be 1.07. So now we've got our A, we've got our B, we're ready to write the equation. Y equals 550 times 1.07 to the power of x. Part B asks, how many squirrels are there after 5 years? So we just want to plug in 5 into x, and then we'll use our calculator to evaluate that. So what we want to type in the calculator is 550 times 1.07 to the power of, oops, not x, but 5. And this is something you just want to type in the calculator. I'm going to go ahead and bring up my calculator. You don't need to raise 1.07. You don't need to multiply that by itself 5 times by hand. I'm not that mean. I wouldn't do that to you. So let's see. Let's pull up this calculator real quick. Turn it on, and we've got 550 times 1.07 to the power of 5. Now you're going to see we're going to get probably a kind of a long decimal here, but we're talking about the population of squirrels. And one of the things we talked about in class was how when you're talking about population, whether it's people, squirrels, fish, whatever, we're always going to round to the nearest whole number. You either have a squirrel here or you don't. You're not going to have like half of a squirrel. It either is a squirrel or it isn't a squirrel. So I'll round to the nearest whole number here. So since I'm rounding, I'm going to use this approximate symbol instead of equals. So we're going to say it's approximately 771 squirrels. And yeah, so that's it for number 10. Go ahead and box this equation because that was my answer for part A. And let's look at number 11. So number 11 says you just bought a new car for $20,000. That's going to be our initial amount, or our A value. And it will depreciate. And you see that word depreciate, that means it's going to decrease in value. So that's telling us we have a decay equation. And the rate is 14% each year. That's the rate here. So the rate is going to be as a decimal 0.14. Now, when you have a decay equation, like I mentioned on the last problem, the way to calculate the b value is it's going to be 1 minus the rate. 1 minus the rate. So we've got 1 minus 0.14. So that's going to be, I think it's going to be 0.86, but since we're allowed to use the calculator here, might as well take advantage of that. 1 minus 0.14. It's going to be 0.86, yeah. Okay, so we got our b value, we got our a value, we're ready to write the equation. So to write the equation, we've got y equals 20,000 times 0.86 to the power of x. Yeah, so there's our equation. Part B says, what will the car be worth after 4 years? So we're going to plug that 4 into x and evaluate that, and it specifically says round to the nearest dollar. So we're going to multiply 20,000 times 0.86 to the power of 4. And we're rounding, so I'm going to use the approximate symbol here. So 20,000 times 0.86 to the power of 4. And I get approximately $10,940. And so that will be our answer for part B. Let's go down here to number 12. It says we've got this function p of t, which represents, scrolled too far. It represents the population of a small town. So the first part says, does the function represent exponential growth or exponential decay? And we can see because that b value right here is greater than 1, then we can say it's exponential growth. What is the yearly percent change in population? So if the b value is 1.5, and we know that for growth, the b value is 1 plus the rate. So 1 plus the growth rate is going to be 1.5. If I subtract 1 from both sides, I get r equals 0.5. So as a percent, the yearly percent change is going to be plus 50%. So it's a 50%, I guess maybe a better way to say this would be 50% growth. Part C says how many people are living in the town after 3 years. So we're going to substitute this into t. We're going to substitute 3 for t and evaluate that. So we have 2,000 times 1.5 to the third power. And we're going to have people here, so actually, I bet this is actually going to come out to be a whole number. I'm going to actually write equals here because I think that's going to work out nicely. So let's see. Let's go ahead and type that in. We've got 2,000 times 1.5 to the power of 3. So we get 6,750 people. Yeah, this doesn't say thousands or anything, so that is just the population. And there's number 12. So let's go on to number 13. On 13, we are just doing some matching here, really just analyzing the percent growth and the percent decay. The first one, we see that we have 1/2. That's less than 1, so that means this is like 1 minus r. And actually, I think what I'm going to do here is go through each one before I actually calculate the percents and make a note of whether it's growth or decay so I know how to calculate the rate. So 2 is bigger than 1, so that means we've got 1 plus r. 0.8 is smaller than 1, so that'd be 1 minus r. This would be 1 plus r because it's growth, it's bigger than 1. And then down here, this is also bigger than 1, so it's 1 plus r. So we've got 2 decay functions and 3 growth functions. So we should have a decrease for these first 2 over here on the top left, and then all the rest ones should be increases. So one way to kind of think about the rate, like on the last one, I sort of just worked out this little equation. Let me scroll back up a little bit so you can see. I set up equation 1 plus r equals the b value and then solved for r, which you can definitely do here. But another way to think about it is just to find the difference between the number that you see and 1. And if it's smaller than 1, it'll be a decrease. If it's bigger than 1, it'll be an increase. So like the first one is 1/2. And you think, okay, well, how far away from 1/2 is, or I'm sorry, how far away from 1 is 1/2? So the difference between 1 and 1/2 is, well, 1/2, which would be 50%, okay? But is it an increase or a decrease? Well, since this number is smaller than 1, we know it's a decay function, so it's got to be a decrease. So this is going to be choice B. Then for the next one, I'm looking at 3 times 2 to the x, and 2 is exactly 1 away from 1, right? 1 plus 1 is 2. And so 1 as a percent is 100%. Since it's growth, it should be choice E, 100% increase. Now the next one is the last decay problem, and 0.8 is exactly 0.2 away from 1, so we know it's going to be a 20% decrease. So that'll be choice F. All right, so just to kind of go back here, this is going to be like, 1/2, 1 minus a half is a half, 1 plus 1 is 2, 1 minus 0.2 is 0.8. For the next one, 1 plus what is 1.5? Well, that would be 0.5. 0.5 as a percent would be a 50% increase. So that would be choice C. And then for this last one here, we've got 1.2, which is exactly 0.2 away from 1. And since it's above 1, we know it's growth, so it's going to be an increase. So we should have a 20% increase. That means this last blank should be G. So yeah, that's all in number 13. Let's move on to number 14. It says the population in Mexico was 126 million in 2022 and is expected to grow by approximately 1.4% every year. Write an equation that you could use to predict the population in millions of Mexico in 2030. So yeah, it's just asking to write the equation. I might just go ahead and take it a step further and find the population in 2030 just so I can show it to you. But I think, going by the wording in the question, it's just asking for the equation. But anyway, so our initial amount is going to be 126. We have a growth equation here, and the rate that it's growing by is 1.4%. So my B value is going to be 1 plus 0.014, right? The rate is going to be 0.014. So let's go ahead and write the equation. Y equals 126, and that's in millions, times 1.014 to the power of x. And I think that kind of satisfies what the question's asking, but just to take it one step further, to go above and beyond, I'm going to go ahead and find what the population is in 2030. So 2030 is going to be 8 years after 2022. So what we want to do here is substitute 8 in for x. So I'm going to say 126 times 1.014 to the power of 8, and I'll throw that in the calculator. 126 times 1.014 to the power of 8. This is a population question, so we're going to round to the nearest whole person. So we're going to say approximately 141 million people. That is a lot of people. But yeah, I think really the answer to this question, it's just saying write the equation. I think this is our equation. We can use this to predict the population in any year. So the second part, it's really not asking for, but just in case you get a question where you do need to actually evaluate that, I wanted to go ahead and do that for you. Number 15 says the graph represents the value of a boat after X years. Part A says write an exponential function to represent the value of the boat. So there's two things we need, right? We need our A value and we need our B value. The A value is the y-intercept, or the starting value. And so if we're looking at the graph, we can see our y-intercept is right here at 0, 30. So my A value is going to be 30. To find the B value, you need to find what the multiplier is. And to do that, you want to divide any of the entries, any of the y values by the previous y value. So like in the calculator here, I'm going to do 24 divided by 30, right? So 24 is the value in thousands of dollars after 1 year, and 30 was the initial value. So if I divide those, I should get my multiplier here, which is 0.8. And so now I've got my function y equals 30 times 0.8 to the power of x. Part B says find the value of the boat after 8 years. So I can, I look at the graph, but you can see that you're not going to be able to tell just from the graph. I do need to plug in 8 into x here. So I've got 30 times 0.8 to the 8th power. This is something I'm not going to do by hand. No way. So 30 times 0.8 to the power of 8. It says round to the nearest dollar. So I'm going to say that this is approximately $5. Oh, wait, no, it's in thousands of dollars. So it's approximately 5. So the question, though, in context is saying find the value of the boat. So we're going to say approximately $5,000. Well, hold on here. Let me think about this. If we're rounding to the nearest dollar, we're actually we want to take this out to 5.033, because when we actually convert it to dollars, because this is thousands of dollars, and it asks to round to the nearest dollar. So instead of running 5,000, I'm going to write 5,033. All right, so there is number 15. So that, I think, wraps up all of these percent increase, decrease, these exponential growth and decay problems where you have like a population growth or the value of something decreases or something like that. Starting with number 16, we're getting into half-life problems. Number 16 says the isotope Ra, radium maybe? I'm not really sure. 226 has a half-life of 1,620 years. How many grams would remain after 1,000 years if there were initially 10 grams, round to the nearest thousandth? So the thing about these half-life problems is to know how to set up the equation up front. Normally when you write your exponential equations, they're going to be in this form a times b to the x. And for a half-life problem, the a value is still going to be the initial amount. B is going to be half because it's a half-life. But the tricky part is to rewrite the x as the time divided by the number of half-lives. Or not the number of half-lives, rather, but the length of a half-life. So we're going to go ahead and substitute in all the relevant information here, and we'll throw everything into the calculator and hopefully get the right answer. So it says that the initial amount, there was 10 grams, so y equals 10 times 1/2, right? And actually with these half-life formulas, b will always be 1/2. To the power of, and let's see, we're going for 1,000 years, and the half-life is 1620, so 1,000 years over 1620, so not quite a full half-life. So just like as far as estimating goes, if it was exactly 1,000 years, if it was 1,620 years, then it would be exactly 5 grams remaining because it'd be half, right? So since not quite that many years have elapsed yet, we know that there's probably going to be more than 5 grams here. So let's see, maybe 6, 7, somewhere around there probably, but let's go ahead and evaluate this. 10 times 1/2 to the power of, and then just make sure you're using this fraction function if you have it available. And just make this go a little easier. 1,000 divided by 1620. So yeah, we get about 6.5 grams. So approximately 6.51, it says rounded to the nearest thousandth. The next decimal is a 9, so we're going to round up to 5.9 grams. So there's number 16. Let's take a look at number 17. It says the isotope C14 carbon. I'm kind of just guessing on these. My background is not in chemistry. But anyway, it has a half-life of 5,730 years. How many grams would remain after 10,000 years if there were initially 20 grams? So very similar problem here. It's the same kind of setup here, and I'll just rewrite that equation. It's going to be the initial amount times 1/2 to the power of t over h, where t is the number of years and that have elapsed, and h is the length of the half-life. So for this one, we have initially 20 grams, so 20 times 1/2 to the power of the length of time, what was it, 10,000 years, and the half-life is 5,000 years, so, or 5,730 years. Clean that up a little bit. Try to make this a little bit more legible for y'all. All right, so 5,730. Since 10,000 years is more than one half-life, it's almost 2 half-lives. Not quite, but almost. So if I cut 20 in half twice, cutting in half once would give me 10, cutting in half twice would be 5, but we're not quite at 2 full half-lives with 10,000 years. So I'm going to actually estimate, we have a very similar answer to the last one, that we have something just slightly more than 5. So probably around 6, 7, something like that. So let's see what we actually end up getting here. We're going to type all this into the calculator. 20 times 1/2. To the power of, I think if we have another problem like this, I might just like copy and paste the previous equation so I don't have to keep doing all those fractions. 10,000, make sure you have enough zeros here, 3, and then 5,730. All right, so there we go. We get, very similar number here, 5.96, and we'll round that up to 6 grams. So that's how many grams would be remaining. That's a long half-life. Yeah, I guess this isotope takes a long time to break down. All right, so that's all the half-life problems. Pretty straightforward as long as you are comfortable with this formula. But now let's get into the compound interest problems. So here's the compound interest formula, and I am going to give this to you on the test. You do not need to memorize this one. Let's see here. All right, so number 18 says you deposit $675 in a savings account that earns 6% interest compounded monthly. What is the balance after 3 years? So first, let's fill in all of the parameters here. Now in this equation here, the p-value, that's like the a, that's your initial amount. Okay, so this is the initial amount. Within the context of calculating interest, the reason why it's a p there is it stands for principal, which is like if you take out a loan, the principal is the amount that you take the loan out for. It's the initial amount. N is going to be, and we see there's 2 n's in this formula, is going to be the number of times interest is compounded per year. Okay, so like, for instance, this one, it says it's compounded monthly, so there's 12 months in a year, so that n value would be 12. R is going to be the rate, and then T is going to be the number of years. That's like our X there. Okay, so it says you deposit $675 in a savings account, so that's 675, that's going to be our initial amount. That's going to be, in this case, our P value. It says it earns 6%, so P is 675, and if it earns 6% interest, that's going to be our R value, and we'll write it as a decimal, 0.06. It says that interest is compounded monthly, So that means my n value is going to be 12. What is the balance after 3 years? So that'll be my t. T is 3. So we've got all of our parameters ready to go, and now it's just a matter of plugging everything into the calculator. So y equals 675 times 1 plus r over n to the power of n times t. And we're just going to put all this in the calculator. This is not something that you want to do by hand. So let's see, 675 times 1 plus, and I'll create a little fraction here, 0.06 divided by 12 to the power of 12 times 3. And so the balance, we do have to round here. It doesn't say like to the nearest dollar or cent. I'm going to go to the nearest cent here and say that it's $807.76. If it asked for the amount to be estimated to the nearest dollar, you'd say $808. Okay, well, let's do number 19 then. Let's scroll down here. It's going to be a very similar problem here. It says you deposit $1,000 into an account that earns 3% interest compounded quarterly. Okay, so let's start breaking down the parameters here. So $1,000, that's going to be our p-value, our initial value. 3% is going to be our rate, and as a decimal, we can write it as 0.03. It says that interest is compounded quarterly. So since it's compounded quarterly, that means our n value is going to be 4, because there are 4 quarters in a year. And then it asks, what is the balance after 10 years? So my t value is going to be 10. So let's fill everything in. Same thing as the last problem. We're just going to plug everything in and then put it in the calculator. So we get 1 plus 0.03. Oh, wait, I forgot the a. Let's throw that in there. Oops. So yeah, we don't want to start with $1. We want to start with $1,000. So 3% over the number of times it's compounded, which is 4, raised to the power of 4 times 10. So let's go ahead and put all this in our calculator. Again, it doesn't say what to round by to, so I'm going to go to the nearest cent again. I think what I'll do here is actually, well, oops. Let's see, 1,000 times 1 plus, create my little fraction, and oops, I guess I lost a plus there. Let's delete this. So 1 plus 0.03, all divided by 4. To the power of 4 times 10. Okay, there you go. We get $1,348, and we'll round up to 35 cents. That's number 19. Number 20, it says you take out a loan for $30,000 that charges 5% interest compounded annually. So in this one, our initial value is the $30,000. The rate here is the 5%, that'd be 0.05. It's compounded annually, so here n is just 1. Annually just means once per year. If you completely pay off the loan in 5 years, what was the total amount of interest you paid? Okay, so the question here is a little bit different. We still have to go through the steps that we did in the last 2 problems, but this is strictly asking for like how much extra you had to pay. So you take out this loan for 30 grand, and then the bank is going to charge you interest for paying back that loan, and so we're going to find out like how much extra money you had to pay for that $30,000 loan. So we'll get a number when we plug everything into the calculator that's more than 30,000, and then we want to find the difference between the principal and the interest and the final amount. So first, let's write our equation. Y equals 30,000 times 1 plus the rate, 0.05, over the n is just 1 here, So we really don't even need to, when I plug it in the calculator, I'm not even going to bother putting that in as a fraction. Dividing by 1 doesn't change anything. So, and then we have 1 times 5. So how much are we going to actually pay the bank back? Let's find out. We've got 30,000. Obviously, we have to give them the money they gave us, but we also have to give them back some interest. So I'm just going to put plus 0.05 because dividing by 1 doesn't really do anything. And then multiplying by 1 doesn't do anything either, so I'm just going to do to the 5th power here. And so the amount that we give the bank is 38,288. But the question here is just how much interest do we have to pay? So if we had to give the bank back 30,000 plus some amount, and that is $38,288, then the interest we paid is the difference between there. So the interest is going to be the amount we actually gave the bank minus the loan amount. Okay, so the interest we paid is $8,288.45. So basically what this means is that, there you go. Having a little delay here on the text. What that means is that basically you had to pay the bank a little over $8,000 to take out a $30,000 loan if you're going to pay it over 5 years, which is pretty common, for taking out a loan for a car. 5 years is a pretty typical length of time to pay them back. You want to try to get that interest rate down as low as possible, so you have to pay as little interest as possible. So I know you don't really have a whole lot of control over that, but just something to think about when you're starting to look at buying a car. Okay, last question here. Credit card company. You got to be real careful with these credit card companies. Whenever you take out like a line of credit with a credit card, the interest rates are normally pretty large. Okay, so here's an example. You take out a credit card that has an interest rate of 24%. Okay, so that means the R value is going to be 0.24, compounded monthly, so my end value is 12. If you spend $24,000, that'll be the principal, or the initial amount, and you don't make any payments during the year, how much will you owe the credit card company? So, in other words, yeah, we're going to have to pay it back. Let's find out how much that'll be. So, 24,000 times 1 plus the rate, 0.24, divided by, 12, and then to the power of 12 times, let's see, what was the year? Was it just 1 year? In a year. Okay, so in a year. So that means that t is just going to be 1. So times 1. So let's go ahead and throw all this in there. You're going to hopefully be pretty shocked at how much you're actually going to give the bank or the credit card company for taking out this credit card. This is going to be a good lesson why it's important to make your payments on time and really try to pay off your credit card each month. Because once this interest starts accruing, it is super easy to start getting underwater, especially with rates this high. And this is not too uncommon with credit cards. All right, so to the 12th power. Okay, so look at that. Oh gosh. So in order to spend $24,000, you're going to basically have to pay the credit card company in this scenario around $6,000 extra dollars, which, if you paid everything up front, made your payments on time, you would only have to pay, the $24,000 back. So something to think about. Anyway, that's going to be our answer for, let's put a little dollar symbol on there. That's going to be our answer for number 21, and I think that's the last one. So, yeah, no more problems. That's it for today. Y'all have a great day.